Okay, so there's one more section in chapter 7, which is essentially it's the bulk part of this unit, but it's one last little application, and essentially it links together our concept of circular motion, which we've been talking about, rotational motion, going in a circle, and correlating that with a straight line, which I kind of ended the last section talking about, but we're going to talk about that a little bit more, and then we'll be done with chapter 7. So if I were to have a wheel going or rotating as it goes down the road, if I were to look at the center of mass of that wheel, it would follow this nice, straight, linear path. And that's why we can approximate information about kinematics and using the formulas that we have with something like a car, even though a car is a very complex object. However, if I were to examine the one point of the wheel, so like this point right here, as it travels through, it goes through this arcing motion because as it travels around in a circle, and then relative to the ground, it follows this nice little path. So when an object rotates about an axis that's going in a straight line, rolling motion is a way to combine the concept of linear motion and rotational motion together. So if I think, this gets a little bit confusing, but the velocity of that object is its displacement over the time, over however long it's traveling, the time interval. But at the same time, the circumference of the circle is the distance that it travels in one period of motion. So here we're starting with this little point at the bottom here, and as we track it, it becomes the point at the top, and then it'll go back to becoming the point at the bottom as it rotates in that circle. So the overall position is our delta x, and that's measured from the center of the circle. But in one revolution, it also goes one full circumference. So since omega is 2 pi over the period, that's its angular velocity, we can also relate the linear velocity based on the angular velocity. And like I said, this is kind of how we ended the last section, but it's just proving that a little bit more mathematically. In physics, this is known as the rolling constraint, which is the link between translational and rotational motion for objects that rotate without slipping. And this is one of the missing pieces of the Great Race Lab, because our tangential acceleration, how fast it moves linearly, is based on the angular acceleration, but it's not only based on the angular acceleration. So that's what kind of relates these concepts back together. So in rolling motion, when I examine one single point, the object is going straight forward with some speed, but one single point actually gets kind of interesting. In translational motion, we say the whole thing is moving forward. But in rotational motion, the top side is moving forward while the bottom side is moving backwards as it's rotating. So if I combine those two things together, if it's moving forward and not just rotating, then it's moving forward with some velocity, but the top side of it is moving forward with twice the velocity, and the bottom side is instantaneously at rest, which is a really interesting concept, but that does kind of make sense because then technically your average velocity would be the velocity of the object. So the top is moving faster, the bottom is essentially stopped instantaneously because it's switching directions, and the middle is going forward with some velocity of omega times r. So here's a quick conceptual example that I'll talk about in class, but it says your diameter of the tires, when you're taking a car, you take a 60-mile trip at 45 miles an hour, the diameter of the tire is 0.6 meters, and we're curious about the angular speed and how many times did they revolve. And we can use this concept of V equals omega r to get our angular speed, because we'll get our linear speed, right, 45 miles an hour. So the first step for part A, we'll get 45 miles an hour into meters per second. And then we can use our quick little translation to get that. And then in part B is how many times that they revolve. Well, once I have angular velocity, I'm actually going to figure out our delta theta, because that'll give me my change in radians. And then my delta theta divided by 2 pi will give me my number of revolutions. So we'll take a look at that in class. But that is your quick little introduction into that. Like I said, and we'll talk about some of these examples in class, but there are a lot of applications that are useful applications. Huge one being robotics. If you have a motor on some type of automated machine, like a robot, and you want it to go forward, you can't tell it to go 5 meters. Like a robot doesn't necessarily know what 5 meters is, regardless of how you program it, unless it's got some type of sensor that puts it on some type of coordinate system. So you have to use this concept of rotational motion, and you don't say you go 5 meters, your wheels need to turn 10 times. And then if your wheels turn 10 times, well, those 10 turns, that's 40 pi radians, and we can use our formulas to figure out that distance then. So there's some really nice or interesting applications of this and converting back and forth from rotational motion into linear motion. But that was just your quick little introduction right now. Our next chapter is chapter 8. That's part of this section. It's going to get into a couple random applications and a couple other things that come up, I guess, including tensile strength, which is an interesting application, as well as we'll take another quick look back at Hooke's law, and we'll do that in the next section.